Okay. This chapter in my textbook is 7, and yours it's chapter 6 and 7 around. And it's the difficulty I'm going to have with this one is I'm going to reference the periodic table from time to time, and it's over there, not on the screen. So it's, you have use your, if you view this thing later, you have to use your imagination. But we're going to talk about atomic structure and periodicity today, and they're intimately related insofar as the periodic table is structured so that it adds some logic to the way the electronic structure of each atom is built. And if you know the way the periodic table is arranged and the logic that's behind setting it up the way it is, it's fairly easy to draw the electronic structure for any atom or ion for that matter. Okay, the key to what we know and understand about elements is the information is delivered to us by light, predominantly. There are other more exotic methods that are used now, but for all intents and purposes, what we know up to this point is delivered to us through electromagnetic radiation, which is another name for light. And the clue to the fact that electronic structures and elements are different is the different colors that they emit or absorb when they interact with light. The first obvious question is, why do we get colors? Where do colors come from? And that first slide had pictures of fireworks. And fireworks are wholly dependent upon the way certain elements emit light and the wavelengths of light that they emit when you excite them. And by exciting, I mean in explosion. And we're interested in knowing why do different chemicals give us the different colors. Now, eventually, we're not going to do it in this chapter, but maybe not even in this course. But eventually, the things that we learn about chemicals and the way they emit colors can inform our understanding of complex molecules, not just elements. For instance, I did my master's thesis on crawfish processing waste. If you've ever seen crawfish, it's kind of like a little lobster, and they're usually red, especially after they've been cooked. That red color is due to an organic molecule, and it doesn't reflect red light because of its elemental electronic structure. It's the way that the atoms interact in that whole structure. So but we know it reacts that way. We know it produces colors that way because of the beginning understanding of how elements absorb and emit light.
Blue ones.
I'm sorry?
There are blue crawfish in the world.
Uh-huh.
I
Yeah.
saw a purple one in my house.
Now that's in the living state, right? Have you ever caught one and cooked one?
I never cooked one. No, I fished with before.
Okay. Are they little ones like this?
No, I caught
Big
one
ones?
guy.
Okay. The kind we used to eat in Louisiana were about like that, and the tails were about that long.
I've seen them that big before, yeah, but not very many of them get that big around here. We usually catch our fish.
Yeah. Plus the winters are cool, you know, and they in Louisiana we've got 363 out of 365 frost-free days. So they have a pretty easy going of it.
Yeah, we never ate one. I told my parents about people eating them before, and they made their face.
Really? Yeah. The only thing that I wouldn't do, since I wasn't born and raised in Louisiana, the only thing I would not do is suck the heads.
Yeah, that's always seemed weird to me.
Yeah. And all you're doing is you're sucking out the hepatopancreas. That's the anatomical structure that's in there. And I guess it has some flavor, but it's just the thought of it. To me, it's like eating cottage cheese.
Makes me think that you're eating a brain.
Yeah, yeah. Mhm. Anyway, so the more we know about the way electrons behave in atoms, the better we can understand how electrons behave in molecules. So we need to gain an understanding of electromagnetic radiation. It has three characteristic parameters that define light. One is the wavelength, and we designate that with a Greek lambda. That's a small lambda. And then frequency is usually given, I've seen it more often now as a small f. I think that's just to simplify things for non-scientists. But we typically use the Greek letter nu in U. So you can see it both ways. And then speed, of course, is, well, for light, speed is c. Speed of light in a vacuum. 2.9979 times 10 to the 8th meters per second.
How many numbers of 5 do you know?
Oh, not many. I never have had to use that one as much. 3.1417, as far as I go.
I think it does 3.1417 something.
Oh, you got me beat.
I don't even think that's the one after saving. I feel like I can't remember. I just know the only one that I know for a fact is 3.14. 3.141. That's all I know.
Yeah.
So okay.
Oh, our calculators, you could probably get it out of your calculator then.
I don't know. I don't know if it gives you a whole number. It probably might.
You could just say, oh, this is my phone. Where's my calculator?
Don't almost go on forever. Or does it go on forever?
Yes, it's a non-repeating. You're testing my memory now. Rational, I think it's a rational number, but it's non-repeating prime. And if I say, let's see, can I do it this way? Where's my pi key? Here it is. Okay, so it depends on how many decimals you called up. But this one is actually, must have changed since my childhood. 3.141593.
And probably rounded it up.
Yeah. Anyway, back to the topic. If we know these three parameters, we can describe light, and we can describe different colors of light. Okay, so there's the wavelength, there's that Greek letter nu, and there's the speed of light. Excuse me. These three are related by this formula. And C, in this context, is taken as a constant. This is the constant speed of light in a vacuum. Now, in other substances, that speed will change. And if you took my physics course, you'd find out how to deal with that too, unless you already had physics. How the speed of light in different substances relates to the refractive index of the substance. And the highest refractive index of naturally occurring substances is diamond. Now, we've made some that have a higher index of refraction in the laboratory, but that's the naturally occurring, that's the highest one. Okay, so this is how they're related. And that means that if C is in meters per second, then lambda and nu have to be, lambda has to be in meters, And nu has to be in reciprocal seconds, right? Because it's in the denominator over here. So that's the way we write S to the minus 1. But we also have another, and it's coming up in a minute, have another expression for this one. We need to define what that means. I'm just saying these are SI units. And those are the ones that if you have these in different units, especially wavelength. Wavelength, this is the SI unit, but typically you'll see it as nanometers. I mean, that's the way I used to use it in the lab. But if you do any calculations with it, you got to change it to meters. And you have to know what nano means. 10 to the minus 9. Yeah, really tiny. Okay, so what do we mean by, well, let's see, which one is this? Okay, here's wavelength. Wavelength is the distance between two crests. And this is true not just for light, but for any wave. Wavelength. You could sound, waves on the ocean, whatever. The distance between two wave crests. Actually, it's the distance between any two similar positions on the wave. So you could go from this one to that one. You could go from this one to that one. Still be the same distance. It's just convenient to say crest to crest. And notice also that what the frequency means. Frequency means how many waves pass a fixed point in 1 second. So it'd be waves per second. But waves it's not a recognized dimension. So that's why we only say reciprocal seconds. And the equivalent of that is hertz, in honor of, I forget his first name, William Hertz. Yeah. So this is also hertz. But that doesn't do you any good when you need to do a calculation like this, right? Hertz just kind of gets in the way. So if you're going to do a calculation, you got to stick in the right value. And notice that as the wavelength gets shorter, the frequency gets higher. They're inversely proportional. And mathematically speaking, you can see that from the equation. If this is constant, then if this one goes up, that one's got to go down. They're inversely related. Okay, this is the electromagnetic spectrum, as far as we know. Of course, if you're a Star Trek fan, there are other forms of light and energy that we don't know about, and they bring them up in the script. What is that? One of my favorite, theta radiation. What's that? I don't see any thetas up here. Anyway, the visible spectrum, the wavelengths or the frequencies, whichever the case may be, that we can detect with our eyes is very narrow. Right here. Right. And it's between 4 and 7, roughly speaking. 4 and 7 times 10 to the minus 7 meters. Or I like to say 400 to 700 nanometers. It's just easier. But anything with a longer wavelength will be over this direction, and anyway, a shorter wavelength will be this direction. So we go from, did they have you memorize the Roy G. Biv before?
I did, I forgot.
Red, orange, yellow, green, blue, indigo, violet. Yeah. Those are the colors of the rainbow from the red end to the violet end. If we go longer wavelength than red, you get the infrared. Right? Normally associated with heat. Right? That's those lamps that keep your French fries warm until they serve them. Those are infrared lamps.
I always think of it as whenever people look through scopes and they see the the heat, it's due to the heat thermal.
Oh, yeah, yeah. Uh-huh. Right. That snipers use.
Yeah.
Right.
Infrared stuff.
There's another dead heat source.
Yeah.
And then longer wavelengths go to microwaves. So this is where you'll find your, where you heat your food. And then longer than that are the radio waves, and they have several subdivisions too. FM is the shorter wavelength, AM is the longer wavelength, and shortwave is in the middle. Shortwave is useful, has been found to be useful for ham radio operators because it travels so far. It goes beyond the horizon. And it does that because the Earth is surrounded with the upper atmosphere, the ionosphere. And they call it an ionosphere for a reason, because the solar radiation ionizes the upper layer of the atmosphere. And it forms a perfect barrier for wavelengths. So here's the surface of the Earth, and you have an antenna up here that's broadcasting. It'll go up there and bounce down here like that. So that's what the short waves are good for. AM, to a limited extent, also does that. On the morning, when I drive here, it's dark, and the sun hasn't ionized the air to interfere. So I can pick up WSB radio 750 from Atlanta, and that's what I listen to on the way.
So whenever I go to Tennessee, we listen to stuff from West Virginia almost over there, but that's because we're in the tri-state area almost over there. When we get to Tennessee, we pick it up sometimes when it's supposed to.
And I can remember growing up as a kid in Tennessee and Georgia, picking up Chicago stations.
That's almost on the other side of it.
It's a long way, yeah. But beyond the horizon, definitely. Shorter wavelengths, ultraviolet, right? You give different sections of ultraviolet. For health reasons, they divide them into UVAs and UVBs based on their physiological effect. And then shorter wavelength than that is X-rays. Right? We use those for what do they call that? Non-invasive diagnostics. Yeah. X-ray, the use of X-rays now on humans is much, much safer than it used to be. You used to have to use higher doses because the film would have to be exposed properly. Now, and first thing they did was made more sensitive film, so you use lower dosage. And now they've got electronic devices pick it up at even lower radiation levels. So it's much, much safer than it used to be. And then the most energetic light waves in the universe are the gamma rays. And if you follow anything, even in the popular news about threats to the Earth, you know, you get meteorite crashes, you'll get.
I see those a lot on the news page about how big one's getting ready to pass the Earth. I see one of those every year.
Yeah. In fact, I heard about one this morning that landed in Australia, went through a roof of a house and missed a woman's head by that much when she was laying in bed. And it was like that.
Yeah. I just made a big old flat. Those things.
Yeah. But the other thing, what I was saying about gamma rays is there are certain phenomena, certain occurrences in the universe that are so energetic. They kick out huge directional beams of gamma rays. They're called gamma ray bursts. And if they're directed toward you, they've still got enough energy, even though they're light years away, they've still got enough energy to strip the Earth of its atmosphere.
I think gamma rays, something like radiation sort of.
Oh yeah. Oh yeah. When it penetrates your body, it'll damage your cells. Yeah, it'll damage your DNA. It's just like being exposed to a Chernobyl disaster. Okay, so that's the spectrum. And in general, as you go from the long wavelengths to the short wavelengths, the energy that's contained in the light beam increases. We're going to calculate that in a minute.
Is that a potato or a pickle?
That's a pickle with a high voltage direct current making it glow.
I didn't hear the top of it.
Yeah. The whole point of this slide is to show the interchangeability of energy. Right? Electrical energy can be converted into light. Well, that's what's happening in these fluorescent light bulbs. And Edison's first light bulb was incandescent, and for a long time, incandescent was the only thing we had available. But they were very inefficient. They produced light of a pleasant glow, kind of a yellowish glow, but they made a lot of heat too. So we used to use light bulbs if we needed to keep a doghouse warm in the winter. They just put a 100-watt light bulb in there, and it would have enough waste heat to keep the dog comfortable in the harshest winter. Okay, so this energy that the light contains is called is it here? Well, it's a quantum, but it also has a name called photon. And so a photon of light contains a certain amount of energy. It's a packet, and it's quantized. And that just means that it either is this much or it's that much and not in between. That's what quantum means. And it is proportional to this value. So E equals H nu. This one is frequency, right, in hertz or reciprocal seconds. And this is Planck's constant. Let's see. It converts this into units of joules. Okay, Max Planck proposed it and is given credit for developing that. And all of this occurred at the beginning of the 20th century. A lot of these advances took place in that time frame. His work, Niels Bohr's work on the structure of the atom, Albert Einstein, and his work in relativity took place in the early 20th century. There you go. So there's I spelled it right. Max Planck. In fact, there's a research institute named after him in northern Germany. Max Planck Institute.
That's such a unique last name.
Yeah. Yeah. So these streams of particles, these photons, each photon contains energy in this proportion, the constant times frequency. And if we say, keep that one in your mind, and then we've already learned this one, which is lambda times there, then we can, if you know the frequency, fine. If you don't know the frequency, then you can plug it in this formula and find out what the wavelength is, or we can combine it. Right? We can say the frequency is equal to c divided by lambda, and then plug this in here. Right? H, speed of light divided by lambda, and that's what this is. Oh, and there's the value of Planck's constant. Right? 6.626 times 10 to the minus 34 joule seconds.
That's almost like a mole.
Yeah, it's just the wrong direction. It's minus 34. But it's what we call in the sciences as a proportionality constant. If we're going to say that energy is proportional to frequency, we can't say it's equal until we are able to resolve the difference in units. right? This one's going to be in hertz or reciprocal seconds. And this one's going to be in joules. So we need something stuck in here to make the conversion. And that's what this is. The real, yeah.
I was going to say, do you mind if I run to the restroom real fast?
Sure, go ahead. Do I need to stop talking?
No, I can watch. I'm going to watch the video again anyway.
Okay.
It'll be good.
Okay. So the real genius of these equations that we are introduced to is not their final form, but recognizing the relationship between the variables. Once you see the relationship here, if this is proportional to that, then all you have to do is search for the constant that takes into account their units of measure. And once you do that, then you're off to the races. Okay, so that we don't lose sight of things, we're still talking about light, characterizing light. And the colors that we see in fireworks are related to the wavelength of light that they emit and the energy that each of those photons possess. Now that's going to be the key, because the energy of the photon is directly related to electronic transition in the structure of the atom. When it moves from one position to the other, then that amount of energy is either absorbed or emitted. So that's the connection, this right here, with the movement of electrons in the atom. Oops. Oh, this is probably a flash video, so it's no good anymore.
Why don't they do that?
I'm not sure why they stopped supporting it. You know,
It was just random. One day I got on my computer, so we stopped class. I was like, okay.
yeah, it just. So I've got to look up substitutes. I'm sure they're out there. Just have to find an appropriate one to fit in this slot. The photoelectric effect is what this is describing. And in fact, Albert Einstein's Nobel Prize was based upon his mathematical explanation of the photoelectric effect.
Oh, the equals interest squared.
No, it wasn't even that.
I've heard that one a whole lot.
Yeah, he's famous for that one. But the Nobel Prize came for his work on the photoelectric effect. And he did all this work while he was patent clerk in Bern, Switzerland. He said I haven't heard him say this, but it said that he liked that job because all he did is review patents, and he could get his whole day's work done in a couple of hours, and the rest of the day he could just sit there and daydream, you know, about this stuff.
I'm like that probably, man.
Okay, so, well, in short, the photoelectric effect is if you have a substance, usually a metal, because metals like to give up their electrons pretty easy. So they work best for the photoelectric effect. So when light impinges on the surface here, and it has a certain amount of energy, right, impinges on the surface of metal, if that photon has sufficient energy, it can kick out an electron, right? And it needs a minimum amount of energy to make that electron leave the surface, right? And we see that as a practical application of that is photovoltaic cells. So there's an equivalence of energy here. You have a certain amount of energy to remove that electron, and then any excess energy is translated into momentum for the electron. I think that's what that video is proposing. eventually, Einstein came up with first his special theory of relativity and then his general theory of relativity. And somewhere in there, I think the general theory is when he came up with this equation. He said energy and matter are equivalent in just different forms. And what you'll see from this relationship is that if you have a little bit of matter and convert it into energy, it makes a huge amount of energy because this is a big number to start with. Then you square it. And it just speaks to the dual nature of light. Light, there's been an argument going on for, well, by now, working on centuries. What is light? What actually is light? And one school of thought says it's energy, nothing more. It's just pure energy. Right? Another school says no, it's particle. I mean, it has momentum. I mean, it behaves as if it has mass. And as it turns out, they're both right. And this is the relationship between the two. And it depends. Finally, they had to settle on. It depends on what problem you're trying to solve as to whether you treat light as matter or as energy. Is it a particle or is it energy? It depends on the problem that you want to solve. And as it turns out, all matter has characteristics of energy. That's what this says. In other words, our bodies moving at a certain speed, we can calculate the wavelength that's associated with that movement. Now, for something this big, it's insignificant. I mean, it's such a long wavelength, it really doesn't have any meaning. And that's called, if we don't get to it, if I forget to mention, it's called a de Broglie wave, named after a Frenchman who actually used, let's see, what did he use? He used, I think he used this equation. Only instead of C, he used V. So this is de Broglie's wave. So if you're moving, you don't have to be moving at the speed of light, but if you're moving,
So,
then
would C speed, right? So is would be for velocity.
yeah, V is for
Okay.
velocity. Yeah. That was de Broglie's argument, that anything moving, especially something moving close to the speed of light, but it doesn't have to be the speed of light. It could be any atom, it could be an electron, whatever. It will have a characteristic wavelength. Okay, we start getting information about the atom when we employ spectrographs. That is, devices that will take light emitted by an atom and spread it out into characteristic wavelengths. And initially that was done with a prism. Right? Light would come in like this and then it would spread out like that. Like Pink Floyd, Dark Side of the Moon. You ever seen the album cover? Yeah, it's a prism. It's just like this. Album cover, now it's a CD cover, I guess. I had to buy a second copy of it because that was back when everything was vinyl, you know, and I wore it out. So I had to buy another copy.
I was the moon turn red sometimes, just with a lot of it.
Yes. Yes, it's a characteristic of light when it passes through the Earth's atmosphere. The Earth's atmosphere acts like a prism, and it spreads the light out. And blue is bent more than red. So as the light goes through, blue is bent so much that it just crashes into the Earth. Right. And then the red is longer, so it goes through and it's bent slightly, and that's what makes it to the moon.
Okay. So that's whenever it's blood moon is what they're called.
Mm-hmm.
'Cause I see blue moons a lot, and I see a yellow one sometimes.
And it's largely due to the fact that the moon is not at the same distance all the time. And it's in an elliptical orbit, and that's thanks to Kepler. Told us that one. Kepler's first law, I believe. Anyway, so when we look at these spectra from light emissions from excited atoms, we notice that sometimes, particularly from sources like the sun, but we can artificially produce these in the laboratory, produce a continuous spectrum. They go from red all the way to violet and no breaks whatsoever. And we've learned since then that that can extend into the non-visible parts of the spectrum. But some elements, and actually most elements, if you investigate individual elements, you will see that they produce line spectrum. In other words, if this is 400 nanometers, and this is 700 nanometers wavelength here, then they may produce like just emission lines and nothing in between. And these always occur for that element at specific values of wavelength. Those line spectrum. We also notice that if you shine a continuous spectrum of what we would call white light at the gas of an element that is neutral, it hasn't been excited, but it's just in the gaseous phase, shine the light through it, white light, these will come out, you'll have light here, 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 and these will be black. So the element in that gas is absorbing light in those wavelengths. So you get it either way, be emission or absorption spectrum, but they're always line spectrum. And the simplest one is hydrogen. And we've since discovered the reason for this, and the reason hydrogen has is the simplest spectrum. It's only got one electron. Okay, and this was going to demonstrate that for you. Okay, now the significance for the line spectrum. Once we realized that with that one electron in hydrogen would absorb energy if light were shined upon it, then it would absorb energy at that particular wavelength and only that particular wavelength, because the electron movement in its space around the atom is quantized. That is, it can only move between discrete energy levels. So if we have our proton here and our electron out here, let's see, we did electronic structure yet? We haven't, okay, so we're going to have to do that. Oh, like 1s2, 2s2.
Oh, I don't think you've done it.
We didn't do that yet. Okay, so that's on the menu. So we've got energy levels here around the atom. And the electron can only move between these energy levels, discrete movements. That's quantized. So that means that the only light that this electron will absorb is the light that allows it to go either to here or to here or to here. And that's particular energy that's related to its frequency. Okay, so that's the clue, that's the macroscopic clue, what's going on inside the atom.
That 1s2, 2s2, stuff like that's going to be a pain in the butt. I don't remember that.
Well, it can be if this is your first exposure to it, or if you just have a particular distaste for it.
I don't like it.
But the periodic table is structured to make it much easier.
Yeah, I had to use it every time I do it. I have to figure out.
Okay. So we have a science denier in the midst.
It's so many numbers, so if you're gonna know exactly which one it's gonna be.
Well, did they do the diagonal chart for you?
Yeah, but I didn't use it.
Okay. Well, yeah, you don't need it if you know how the table's structured, and you know the exceptions.
I did, but I forgot one. I was on like 12th grade and I decided not to remember it, and I probably should have.
Okay.
It's not, I just forgot.
Why is it significant that color emitted from the hydrogen emission spectrum is not white? Well, I guess I'm supposed to answer that one. Come on. Why is it significant that the color is not white? It's significant because it is a macroscopic reflection of the movement of electrons in the atom. And it supports the quantized energy levels because you only get discrete wavelengths, which means discrete amounts of energy in the transfer of electrons from different movements. Okay, I mentioned the Bohr model earlier. The Bohr model of the atom is modeled actually after planetary systems. Bohr just said, all right, we got to start somewhere. So we're going to start simply. We're going to say the nucleus is like the sun. Okay? And he kept it simple, working with the hydrogen atom only. And then the electron is out here like a planet. So it orbits.
All the way up to A.
All the way up to what?
The A Valence Electrons, whenever they're happy, stuff like that. Orbitals. You don't understand what I'm saying.
8? Did you say 8 orbitals? No.
4, but like there's 8, but there's gonna be. They have 8 electrons and they're happy, is what I'm trying to say.
Oh, the octet.
Yeah.
Yeah, okay. Yeah, we'll get to that, hopefully. If I don't stop wandering.
That's my fault. I'm sorry. Do you mind if I go to the restroom real quick?
No, go ahead. So, Bohr imagined energy levels around the atom. Right. And the further you get away from the atom, the higher the energy level. Right. Further away, it's kind of like gravity. It takes energy to move me from this height to, say, the roof. It takes energy to move the electron from here out to here. So if that's 1, 2, 3, this electron has made the jump and requires energy to get there. So when it jumps back, it gives up that energy. So there's the difference between absorption spectrum and emission spectrum. Now, the lowest possible energy level, energy state for an electron is known as the ground state. Now, for the hydrogen atom, of course, that'll be energy level 1. That's the ground state. But for multi-electronic atoms, it will be whatever is the lowest energy for all of them. And as we add electrons, we add them low energy, and then we keep moving out. They always go to the lowest possible energy state for its ground state, and any additional ones have to occupy higher levels. So that's the ground state. And if we add energy to that electron and make it bump up to a higher level, we call that the excited state. This is a representation of energy levels. So if you picture the nucleus down here, then the first energy level is very close, but it's never at the nucleus. It's always some distance away, but it's close. And then the second energy level is quite a big jump. And then as you go further out, the distance between the energy levels decreases. They come closer together. For the visible spectrum of hydrogen, the line spectrum of hydrogen, actually there should be 4 here. There's another one that jumps from 6 down to 2. So these are the colors, and they each have a wavelength. And the electron, in order to emit light, will jump between here and here. This will be the lowest energy, or the red one. And then this will be the green one, it jumps 2 levels, and this will be the blue one, it jumps 3 levels. And I think there's a violet one that jumps 4 levels. And this is what it will look like in a circular diagram. This is n equals 1 right here. It's not showing the nucleus. And this is n equals 2, this is 3, 4, and 5. And these calculations can be made and prove that the energy difference is associated with that particular wavelength. Oops, excuse me. But we need the proper equation. And this is the equation that Bohr came up with. The change in energy between the energy levels for the hydrogen atom only. That's the problem with the Bohr model. It only works for the hydrogen atom because there's only 1 electron. When you get more than 1 electron in there, you get interferences. You get multiple protons, you get multiple electrons, and they interact. So it kind of messes with your calculations if you try to go beyond the hydrogen atom. Or an atom that looks like hydrogen. In other words, it only has 1 electron, but it can have several protons. If that's the case, then these values change. Right? If you have 2 protons, then you put a 2 there and a 2 there, or a 3, a 3. But it has to be an ion so that you only have 1 electron. But we're settling on the hydrogen atom here. And this is just one of those proportionality constants right here. And all you need to know is what's the energy level. And that N is also known as the principal quantum number. And it's always related to the energy level. N is, just think, when you see N, think energy. So the change in energy is when the electron jumps between these principal quantum levels. Okay, so here's an example. Say for the hydrogen atom transition from 5 in quantum level 5 to 2, we observe blue light at this wavelength. So if we plug in the values here, this is the initial level at 5, and it jumps to 2. So we square those and take the reciprocal of each and subtract and multiply this value. When we do that, we get this is the energy of that transition. Okay? And if we equate that energy, and this one has a sign on it, because the closer you get to the nucleus, the more negative the sign. Because once you get away from the nucleus to a certain level, infinity, your energy relative to the nucleus is 0. So if this is more negative, then you add energy and it decreases that negative value until you get to infinity, and your energy is 0 relative to the atom. Then you have an ion or a free electron. So that's why the value here is negative. The more negative, the larger the jump. But when we take that energy change and we stick it in our formula here for h nu or hc divided by lambda, we can determine the wavelength of that light. And the one thing that we have to do, though, is to remove that negative sign. This is an absolute value. So we're doing two calculations here. One is we're calculating the energy based on the jump between principal quantum levels. And here we're calculating energy based upon the wavelength of light. So the wavelength is 434 nanometers, which is 4.34 times 10 to the minus 7 meters. And the calculation gives us approximately the same energy as this transition. So there we see the equivalence between the two. Okay. The Bohr model works for hydrogen atoms and for hydrogen-like atoms. So what we're saying with that large negative number is as the electron becomes more tightly bound, that it's closer to the nucleus, right, where it feels the positive charge of the protons in the nucleus more strongly, the value is more negative. And only free electrons have zero energy relative to the nucleus. Okay, the problems, I've already mentioned one problem with, erase that. One problem with the Bohr model is that it only works for the hydrogen atom. And the other problem we've discovered is that electrons do not move around the nucleus in circular orbits. And one of the reasons we know that is, if that were true, when an object is moving in a circle, what's it doing? It's changing direction. Remember, the definition of acceleration is a change in velocity. So you get changes in velocity by one of two ways. You either change the speed or you change the direction. So if the speed's the same, but you change direction, like it's going, at that instant it's doing this one, but now it's doing this one. Right? So if we move this vector over here, then it has changed direction, directed at the center. So that's called a centripetal acceleration, and that bleeds energy. So if that were the case, with circular orbits of electrons around the nucleus, then the electrons would eventually lose energy and crash into the nucleus, if the orbital model were correct, but it's not. Electrons do not move around the nucleus in circular orbits. That's the second fatal flaw in Bohr's model. But what did I say about models? When a model fails, what do you do with it? Well, you can toss it out and start over, okay? Or you can restrict its use. That's what we do here. This is good for under certain circumstances. Or you can modify it. And actually with Bohr's model, we've done both, restrict its use and modify it. Well, actually, the modification is so extensive that it's essentially a new theory. But it doesn't get the ball rolling. Okay, what color of light is emitted when an excited electron and hydrogen atom falls from 5 to 2, 4 to 2, 3 to 2? You can calculate each one of those. All right, we don't have time to do that here. But which one is going to have the redder color or the longer wavelength? Remember when I said red is the lower energy and blue is the higher energy? So the higher energy, the bluer one, is going to be the bigger jump from 5 to 2. And then this will be the green one and this will be the red one. Okay? Blue, green, and red. Yeah, orange, red. Okay. Let's see. Heisenberg's uncertainty principle. We'll say just a word about this. Werner Heisenberg was one of those early 20th century genius physicists. And his work focused attention on the fact that when things get really small, like the electron, like the atom, it is impossible to know both where it is and how fast it's moving. You can't know both at the same time. If you're able to calculate how fast it's moving, then it's anybody's guess where it is. If you fix it in position where it is, then you don't know how fast it's moving. And this is the way it's stated, right? Change in position times the change in momentum, which is mass times velocity. And that's the reason I said change in velocity, because if you're talking about the same particle, the mass doesn't change. It's constant. This term is greater than or equal to Planck's constant divided by 4 pi. Right? So what that means is this value is going to be very small, right? Planck's constant is 10 to the minus 34. This is very small. So if the position, the uncertainty of the position is very large, then the uncertainty of the velocity is very small, which means you can find out how fast it's going, but you can't know where it is, or vice versa. If this is very small, I mean, if the change in velocity, if the uncertainty of the velocity is very small, then the uncertainty of the position is very large. That's what that's saying. So how can we know, like I'm running, how can you know how fast I'm going and where I am? Because my mass is huge, right? And that swamps all the other factors in this formula. So for very large objects, the uncertainty, both here and here, are very small. Okay. Oops. When mass is large, delta X is very small. So you can always know where I am. But when I get very small, you can't know both of them at the same time. Okay. So that brings us to the topic of then, if the electron is not orbiting the nucleus, like a planet, and Heisenberg says we can't figure out where it is, what do we do with it? Well, when all else fails, turn to statistics. Statistics can explain anything, right? You've heard the expression, there are lies, damn lies, and statistics, in that order. Statistics can tell you anything you want it to. But if used properly, it can solve problems. And that's what we use here. In the description, in the function of predicting what region of space an electron may be found, this term is included in that function. It's called the psi, or the wave function. And if we square that function, then that indicates a probability of finding an electron near a particular point in space, right? It's all probability. It doesn't say absolutely the electron will be there. It says it's most likely to be there. And with this information, we can draw a probability distribution for electrons around an atom. So for a 1s orbital, right, with an m equal 1, well, we haven't talked about, hold on a second. Okay, we're getting there. This is a little out of order, but for the simplest, closest orbital to the nucleus, that's the 1s orbital. The wave function says you're most likely to find your electron very close to the nucleus, right here, like that. But it won't be right at the nucleus. It'll be some distance away. And this is a probability curve, right? So the highest probability is right in this section right here at that distance. Now, as it turns out, knowing where the electron is not nearly as important as knowing what its energy is, because the energy of electron determines how it will behave in a chemical reaction. Now, the position, the probability of where it is has a bearing on the reaction, but it's more important to know the energy. Okay. About orbital size. When we're talking about orbital, we're saying, all right, this is the region of space that we're likely to find an electron with that particular energy. Okay. And the psi function that we just talked about tells us the region of space, and relative to that, the size of the orbital. So the energy level 1 orbitals are close to the nucleus, so they're not very big, right? Because the nucleus isn't that big either. So they're the smaller ones. And the size of the orbitals gets bigger as you increase the principal quantum number. Okay, so here we have, in order to describe the energy and location and actually shape of the orbital, you need 4 quantum numbers. And these numbers are, they fit in positions in mathematical formulas to describe the probabilities of energy and position for an electron. If you know these 4 numbers, and we're going to use these 4 numbers to write the electronic structure of an atom and an ion. Okay. Principal quantum number, I mentioned that first. This relates to the size and the energy of the orbital. So the larger the number, the more space is being defined for the orbital, and the higher the energy. Then you have the angular, the L number, the angular momentum quantum number. Okay, this one describes the shape of the orbital. Sometimes it's called the subshell. The shape of the orbital. It could be spherical. Some of them look like dumbbells. Some of them look like donuts. So this describes the shape of the orbit. I'm going to tell you how the numbers work on this in just a minute. Then there's the magnetic quantum number, M sub L, which describes the orientation of the orbital in 3-dimensional space. Okay. Say if it's a dumbbell, is it pointing this way, or is it pointing that way, or is it pointing this way? And then there's the electron spin quantum number. And this just refers to the momentum, the angular momentum, not this angular momentum, but the angular momentum of the electron. So if you think of a spinning top, okay, spinning top, it's difficult to move because their momentum is directed on the axis of the spin. And if it spins this way, it has an angular momentum one way. If it spins the other way, it has an angular momentum the other way. So that's what we think of in terms of the spin quantum number for electrons. Although in reality, the electron doesn't spin like that. It's just a way of keeping track of things. So with these 4 numbers, you can completely describe the electronic structure of an atom. Okay, so how do the numbers go here? Well, the principal quantum number starts at 1 and just keeps going as big as you want it. On up. Okay, till you run out of elements. The angular momentum is a sublevel of each one of these. So to do that, you start with 1, you start with the n minus 1, and then you work your way up in whole numbers. Right, just add a whole number. So for 2, let's do 1. So you start with 0, and that's it. That's all that 1 can have. If you start with 2, then you can have 0 and 1 possibilities. If you start with 3, you can have 0, 1, and 2. So the number of angular momentum numbers you can have for each one of these is the same as the number here. Right? If there's 3, you can have 3 of them there. 4, you can have 4. But it starts at 0 and works its way up. Okay? Then we take each one of these, and for each one of these, you can have minus L up to plus L with whole number increments. So let's say we have 5 here. And we say we got 0, 1, 2, 3, 4. So we could take maybe 3. Let's take 3. So 3 would give you minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. Those are the possibilities in this level. So it's kind of, it's a tree, it's a branch, it's a branching tree. And then the spin can only be plus 1/2, minus 1/2. Those are the only choices. Okay, so now that we know how to extract the various numbers from these levels, you start from here, you work your way down for each sublevel. Once we can do that, then we can start building atoms and plugging electrons into them. Okay, so the N is always numbers, but when we start writing the electronic structure for atoms in shorthand, or writing them out in, dragging the structure out like this, it can get pretty messy if we keep the number for the L's. So we've substituted letters. Right? 0L is S, 1 is P, 2 is D, 3 is F. And that's as high as you need to go, because beyond that, you run out of elements. All right? Okay. It gets easier with practice. Believe me. So for principal quantum number level, N equals 3. N equals 3. Okay? Determine the number of allowed subshells. So those are the L's, different values of L. So we take this one, and L can be what? L can be 0, 1, or 2. Right? So you can have 3 subshells of N equals 3. And then for each one of these, we would say this one is S, this one is P, and that one is D. So if N equals 3, you can't have anything past D. So we can have, well, there it is. We can have 3S, 3P, or 3D. So let's start relating this to the periodic table. If you look at the periodic table, the horizontal rows, the rows are periods. And each one of these periods has a number from top to bottom. And each one of those numbers is related to N. So this is N1, N2, N3, N4, N5, N6, N7. Okay, that's our starting point. For L equals 2, so let's say we have L equals 2 here. What's the magnetic quantum number and the number of orbitals? Okay, So 2 means we can have -2, -1, 0, +1, +2. So we can have 5 orbitals at that level. Okay. These talk about the shape of the orbital, like 1s orbital is spherical. All the s orbitals are spherical. The 1s orbital is simple. It's just most concentrated close to the nucleus and decreases out. The 2s orbital, however, has some concentration close to the nucleus, but it drops to 0 here and then jumps back up here. This is called a node. 3s orbital has 2 nodes. So 1s has no nodes, 2s has 1 node, 3s has 2 nodes. Where the probability of finding an electron in that region is 0. Okay, for the p orbitals, they look like those dumbbells. And, okay, so for the p, what could we have for the m sub l? We could have -1, 0, +1. Okay, and if the shape, if the L tells us the shape, then the m sub l tells us the direction. So this shape of a dumbbell could be pointing on the x-axis, on the y-axis, or the z-axis, x, y, and z. And the D's get even wilder. So there you have different shapes, right? Sort of a complex dumbbell. And then one of them has a donut. So now we're going into areas that I don't even want to touch. But this orientation also helps us understand how reactions occur. Because remember, when two molecules or atoms or whatever the case may be, when they approach one another, they need enough energy for the reaction, plus they have to be oriented correctly. And this is why they have to be oriented correctly. If they're not, then no reaction will occur. So you have to get that overlap of electronic orbitals in order to get the reaction to proceed. And then F is even worse. And these are all mathematically based. They're statistical, right? Nobody's ever seen those. And then electron spin. And this brings us to conditions that have to be met in order for a proposed electronic structure to be valid. This references one called the Pauli exclusion principle. And what it says is that with an electronic structure that's written for an atom, no 2 atoms can have the same. No 2 electrons can have the same set of 4 quantum numbers. They can have the same numbers all the way down to the m sub s. And then one will have a plus half, and the other will have a minus half spin. What that means is that once you get down to that level, when you get down to the m sub l level, say we have a, I don't know, -1. Once you get down to that level, then you can only have 2 electrons in that orbital. One spinning one way, one spinning the other way. Okay. Here's the problem with polyelectronic atoms. Those atoms with more than 1 electron is primarily we don't know where the electrons are, which means we cannot calculate their repulsive forces. So as we're building atoms, think of it in these terms. as you move from left to right and top to bottom in the periodic table, you're adding protons, right? That's what determines an element. And with a neutral atom, you're also adding electrons. And more electrons in this region outside the nucleus, there's more repulsive force with those electrons. They're also feeling some attraction to the nucleus, otherwise they wouldn't be there. And what we have to do is, as we build atoms, add protons and electrons as we move down the periodic table, the electrons always are placed in the lowest possible energy state. Right? We want them in the ground state. Before we do anything with them, before we try to excite them, before we try to react them with anything, we want them all in the lowest possible state, which means that you're packing them in. And you got to fill these orbitals before you can go to the next level. Okay. Penetration effect. This is kind of a difficult subject. If we look back to the diagrams, right, where we had the 1s orbital, was kind of like this. This is distance from the nucleus. And this is probability of finding the electron there. So increased probability close to the nucleus. Then if you get the 2s, you get like that. Okay? You get a node here. And then with the 3s, you get two nodes. It's not quite the scale. The point I'm trying to make is that even though most of the electron density for the 3s electron is supposed to be here, the model says that there will be a small probability that you'll have some electron density closer in. Okay? And that effect of putting some of it closer in is called penetration. And when we compare s's and p orbitals, let's see if we've got a picture. Yeah. Okay. But if we're in the same principal quantum number 2 here, so we got an s orbital in the 2 level has a node right there. Right? So this is the 2s orbital, it's red one. The 2p orbital is here, with most of its electron density right in that region. So even though 2s has a little bit higher energy on its major section, it still has some that is closer to the nucleus than the 2p. Taken all together, that makes the 2s orbital desirable for the lower energy than the 2p. That penetration effect makes 2s lower energy than 2p. Okay. And it works for the 3s, like I drew here. Actually, that's not accurate. It should be down this. This one should be down here like that. And this one should be like that. Okay. So that penetration effect is taken into account when we're judging the energy state of an electron and whether what the electron is overall lower energy than another one. Okay, periodic table, a little history. trying to make some sense of the elements that had been discovered up to this point. This is in the mid to late 19th century. One of the first attempts to organize elements in some logical fashion was proposed by Dobereiner. He found several groups of elements that had similar properties, physical and chemical properties, called them as triads. The best example would be a group of halogens, chlorine, bromine, iodide. They all had similar chemical and physical properties. Actually, their physical properties were pretty different. Chlorine's a gas, bromine's a liquid, iodine's a solid. So it was more based on their chemical properties. And there were other triads. Then nearly the same point in history, Julius Lothar Meyer and Dmitry Mendeleev proposed a structuring and positioning of the elements in tabular form that took into account these physical and chemical properties. The reason that Mendeleev is given the lion's share of credit for developing the modern periodic table is based on one fact. Mendeleev predicted the existence of elements not yet discovered. And he also predicted their physical and chemical characteristics, right down to the molecular weights. So when they were found, that confirmed what he had predicted. So he's given the lion's share of credit. But Meyer did contribute. Mendeleev, in fact, he admitted that he based a lot of his work in constructing the periodic table on previous work that had been proposed by, my mind's gone blank, by Avogadro and one of his students, his disciples, Cannizzaro. They're both Italians. He said they really solved the problem for him and allowed him to construct his table with confidence. Anyway, so when he found his groups, his families of elements, and originally he put his families left to right in his first publication, and then the second publication, he switched them into verticals. But these groups had to have proper characteristics, and when he started lining them up and increasing mass, he found that when he came to a point where the next one had a certain amount of mass and it would have gone in this position, he said, wait a minute, it doesn't have anything like these characteristics. It's more like the one next door. So he just moved it over and said, it's there. And this one is undiscovered. He did that several places. And eventually, those elements were discovered and characterized. Okay, another German word, Aufbau. I don't know German, but I understand that Aufbau means do it this way, in the simplest terms. So the Aufbau principle just says that as you add protons and you're building and electrons to go with it, and you're building successively heavier atoms, as you add a proton, the next electron goes into the lowest possible available orbital. That's all it means. So now that we have this quantum approach to the description of an atom, we can calculate what that next energy level will be. And most of them are fairly orderly. As you follow along in the periodic table, they're orderly. And the electrons will go into the next, what you would expect to be the next orbital. Except sometimes there are exceptions. And those exceptions can be explained logically, but mathematically, they obey this principle. Those electrons have to go into the next lowest energy orbital. And it may not fit what we expect to see. And they occur in places like, let's see, 1, 2, 3, 4, 5, manganese and zinc are two examples where you expect to see electrons in this orbital, but they're not, they're in this orbital. Okay, another rule. So we've got what? The Pauli exclusion principle, Aufbau principle, and Hund's rule. Hund's rule just says that when you have sublevels of your orbitals, for instance, if you have one that requires a 2p, remember, p is L number 1, so that means m sub L can be -1, 0, +1 inside p. If you've got electrons that need to go in that orbital, then as you add protons and you add electrons, they go in like this. Separate them first. And this means spin up, spin up, spin up. Like that m sub s number. And then spin down would be like that. But Hund's rule says that you got to put, if you got more than is required for that level, then you got to put them in separate sublevels first. And then you can go back and start pairing them up. And that's based upon the principle that electrons are negative and they're going to repel. So the lowest possible energy state would be to separate them, keep them in separate orbitals. And you do that until you are forced to pair them up. So that's Hund's rule. Okay, orbital diagrams. Here's where the fun starts. Now your textbook probably does it this way too. I don't remember. So for these orbitals where we're going to put spin up, spin down electrons, they like to draw boxes and put complete arrows. That's too much trouble. Yeah, that's way too much trouble. When I've got a 2p, I just draw a line and put a single arrow. Like that. Okay? Much quicker, much simpler. It doesn't slow you down your thinking process for you to draw the structures here. Oxygen is our example here. So if we look at oxygen, how many protons does it have? And it's 8, right? 8 protons. So with a neutral atom, you're going to have 8 electrons. Right? And we start off with the lowest possible energy level, 1. And remember, with n equal 1, what can L be? L can only be 0. That's it. Just 1 minus 1 is 0. That's it. You're done. And remember, L0 is S letter. So 1s is all that you can have in that principal quantum number level. That's it. Can't go any further. Then if you go down to the next period, you have 2. So you can have 0 and 1. So 0 is S and 1 is P. All right. You go down to the next principal quantum number, 3. Now you can have a 0, a 1, and a 2. And 2 is D. Okay. We may not need all those, but that we can do that. Now we got electrons that we need to put in there. Right? So we got 8 electrons. How many can go in the S? Only 2. 2 electrons. So we've got 2 here, 2 here. We've used 4 of them already. With the P, you got 3 sublevels. right? Because it's 1, it can be -1, 0, +1. And each one of these sublevels can have, right, 2, 4, 5, 6, 7. We got room for one more. And that's it. You're done. So 2, 4. That is oxygen. Okay, that's why it's written this way. And why it's written this way, to obey Hund's rule. Okay. Now, once you've drawn this, if you need to know how many valence electrons there are, valence electron is outermost electrons with the highest energy level, which means the highest N. Count them up. How many are in that level? And those are your valence electrons. So in this case, we've got N equals 2, and we have 6 plus 2 is 8 valence electrons. Okay? There's your octet, by the way. So when you have a complete octet like this, that's a noble gas. So let's see, 6, 8, 9, 10, that'll be neon. 10 electrons. Okay, this is the way the periodic table is structured. So all the elements in the alkaline metals and the alkaline earths are either filling or filled s orbitals. Those first two columns are s orbitals only. They might have other levels that have been filled to get them there, but the outermost electrons are filling these orbitals. In this side over here, and that's true for hydrogen and helium also, they're s orbitals only. All of these are filling p orbitals. And all the transition elements are filling d orbitals. And then stuck right in here, the lanthanides and the actinides, they're filling f orbitals. Okay? So we've got the principal quantum number, and then we've got the L's that are being filled, and then the M sub L's, right? All the S's, they can only have 2 electrons. That's why you've only got 2 columns here. Once you've got 2 electrons, you're done with that level. You're done with this S. Over here, you got 6, because P can have -1 plus 1, -1, 0 plus 1. 2 electrons each is 6 electrons. 1, 2, 3, 4, 5, 6. Okay. These are D's. So if S is 1, 0, excuse me, P is 1, D is 2. So it can have M sub L's of -2, -1, 0, +1, +2. And each one of those can have 2 electrons in it. So if they're all filled, you have the potential for 2, 4, 6, 8, 10. Let's see. I've got too many. Sorry. Wait a minute. 2, 3, 4, 5. Oh, that's 7. Wait a minute. What am I doing wrong?
Counting the addition sign.
Let's do that again. -2, right? -1, 0, +1, +2. There we go. So there we can have 5 orbitals with 2 each means 10. So 10 electrons or 10 protons, which means D's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, starting to make sense. With F's, you can have -3 up to +3, or 7 orbitals, times 2 is 14. So there should be 14 right here. Okay? All right. is that diagonal thing I was talking about before, knowing which ones to fill when. So if you say n equals 1, 1s is all you could put in there. N equals 2, you can have s's and p's. N equals 3, you can have s's, p's, and d's. N equals 4, you can have s, p, d, and f. 5s, you can have s, p, d, f, and you can actually have g's. But when we start filling electrons, we don't need g's. So that's why we just chop it off here. And the reason also is we're going diagonal. So you fill this one, 2 electrons. Fill this one, 2 electrons. Fill this one, 6 electrons. Then you go back to 3. Then you go back up here, 3p. Then you go to 4s before you go to 3d. Okay? That's what that diagonal means. This is the order of filling. As you add protons and electrons to go with it, you fill in that order. Now, what does that look like on the periodic table? Well, this 2s is followed by 2p. 2p. Then you go to 3s and across to 3p. Back up here, 3p. Then you go to 4s. And then when you get into the transition metals, you go to 3d. And then you get to 4p. And then you go back over here to 5s. Now you swing back around to 4d. So this is 4d. And this is 5p. And then 6s. And once you get to 6s, now you're down here. This is where you hit the lanthanides. So once you get to here, you hit lanthanum. Now you're in Fs. And you fill all the Fs, and then you come back out of that one right there, back up to here, and you hit the Ds again. Okay, that's what that means. So you're okay here on the S's and P's until you start getting the transitions. And then this fourth level, fourth level, you go 4s, and then you have to back up to 3Ds. And then you go back to 4Ps. And now you're at 5s, now you go to 4Ds. Okay? And if you know how the periodic table is structured, you can write the structure very easily. How about sulfur? Let's try sulfur. Sulfur's here, 16 electrons. All right? So we're going to have a 1s, a 2s, a 2p, a 3s, a 3p. Let's see. 3p, that'll get us, that's all we need. 3p's. Okay, 16. 2, 4, 10, 12, and 4 more, right? So let's look. 3p4 should be right here. We're filling p's here. We're on the 3, period. 1, 2, 3, 4. There you go. 3p4. Now, how many valence electrons do we have? 6. 6 valence electrons. That's why sulfur, when it's ionized, it prefers a -2 charge. Add 2 electrons. If you add 2 electrons to this, what do you get? Argon, 18 electrons. So it has, this is isoelectronic with argon. It has the same number of electrons and the same electronic structure. Okay, how about barium? Well, barium's a big one. It's way down here. And if you draw barium, let's see. Well, okay. I should have shown you this. If an even shorter way of writing this is to think of it in terms of noble gases as a core. So if you have a noble gas here, neon with 10, then you go beyond that one and you say, okay, now we're down to 3s. 2, and then 3p4. So that's also the electronic structure. We know what the core is like, and then we just want these, because that gives us our valence electrons. And you can do the same thing with barium. We could write it out like this, string it out, all like that. Or you can say, okay, what's xenon? Xenon is, if we go barium and backwards, we go barium, cesium, xenon. And then what do we have left? We have 6s2. That's it. And you know, you see your valence electrons. Europium, where's europium's way down here? That one's going to be a booger. 1, 2, 3, 4, 5, 6. Okay, it should be normal. Xenon. So xenon, just like barium, right? Xenon, and then you add 6s, and now you're into the lanthanides. So it's 4f. 1, 2, 3, 4, 5, 6, 7. I'm not going to throw too many of those extra, because while they're interesting, they're not very useful to us at this level. So we're gonna spend most of our time up here. I should say time and energy. All right. Okay, now we're going to look at periodic trends. No, we didn't define it. I just used the terms. Groups are verticals. Right? They have similar chemical characteristics. And left to right, across the horizontal, are periods. And they're called periods because my best analogy is periodic motion. Have you ever heard of periodic motion? It's like a pendulum. It's motion, but the motion eventually comes back to where it started. That's a period. If you start your pendulum here and it goes out like that, like that, like that, it comes back to the same place. It has moved, but it's back to the same place. So when you think of that period on the periodic table, you're saying, all right, if I go down here like this group has that characteristic, that one, that one, that one, that one, that one, that one, that one. Noble gas. Okay, now we got 19. So is there another group out here? Well, no, because potassium looks like sodium. So we swing back around. We complete the period. Right? So our pendulum has swung, it's come all the way back to here. So that's why they're called periods. All right. So periodic trends. The way the table is set up now, structured that way, we can say some things about ionization energy, electron affinity, and atomic radius. There are other periodic trends, but these are the ones we're going to focus on. They're the most useful for us at this point. We just have to define what we mean by each one of those. Okay, ionization energy is based upon the element, whatever it happens to be, has to be a gas. And we end up as a product with one electron missing, still a gas, and there's your free electron. So in order to get from here to here, you have to input energy. And that's the ionization energy. How much energy do you have to put in to kick off one electron? Now, why do we need a gas? If it's not a gas, then when you put energy into it, some of that energy might go into changing it from a liquid to a gas. Or if it starts off as a solid, you add energy to make the solid turn to a liquid and then to a gas, and then you kick off electrons. So we're really not looking, if this is a solid or a liquid, you're not really getting the story in terms of how much energy it takes to remove an electron. That's why it has to be a gas. Okay? So for magnesium, to remove one electron, it takes 735 kilojoules per mole of magnesium atoms to remove an electron. That's called the first ionization energy. The first ionization energy is always the neutral atom remove one electron. But you can carry this, you can take that ion and kick off another electron if they're available. Right? If it's hydrogen, of course, your job's done. You got nothing but a proton left. But with magnesium, we have some more electrons. Right? So the second ionization energy removes another electron, and it takes more energy. It takes about twice as much energy for the second. Now, why does it take more energy? It's electrostatics. It takes more energy to remove a negative from a positive than it does from a neutral. Okay? But then when we kick off the third electron, think of it this way. Here's magnesium. If we kick off an electron, then the electronic structure looks like sodium, right? Okay. Kick off another electron, then it looks like neon. Now you have a complete octet. And octets are desirable. They're very stable. You got complete, in this case, S&P orbitals to be neon. So if you're going to try to remove another electron from a stable core, it's going to take a lot of energy. And it does. 7,000 kilojoules. 10 times as much as it did to remove one electron from the neutral atom. Anytime you get down into the core, now you're bumping the game up. I mean, you're high stakes poker now. Lots of energy to remove a core electron. And that's the same with any of the elements. Okay. So what is the trend in the periodic table for ionization energies? Okay. If you look at the periodic table and you go from left to right, you see the first ionization energy increases from left to right. And the simple explanation for that is you're removing an electron from a higher positive charge in the nucleus, right? You've added protons going from left to right. So the first electron you remove is fighting against a higher positive charge. So it takes more energy as you move from left to right. As you go down in a group, it takes less energy to remove an electron. The reason for that is that outer electron is further from the nucleus. Right? Even though you've got more protons, you've also got more electrons in between you and the nucleus that are shielding you from that charge. So as you go down in a group, it takes less energy. Or vice versa. If you go up in a group, it takes more energy. Because the energy level of the outer electron is closer to the nucleus. So combine those two. Ionization energy increases from lower left to upper right. As a general rule, right? These are all generalities. Okay. Let's see. Well, these show us some trends. You're always going to have very high first ionization energies for the noble gases because they're perfectly happy right where they are. And then the lowest in a period is going to be to the farthest left, right? Lithium, sodium, potassium, rubidium, cesium. They're going to have the lowest first ionization energies. All right. So why isn't the graph of ionization energies across a row linear? Where are the exceptions? What you're looking at is electron repulsions. Let me go back. Oops. Here we go. So if we're moving from left to right, let's say lithium, here we go. We go lithium, beryllium. And then the first ionization drops down for boron. and then it goes back up to nitrogen and it drops down again for oxygen. So when you're going from beryllium to boron, where is your electron located? Well, here it's in the s orbital, and here it's in the p orbital. So in the p orbital, it's got no neighbors. For nitrogen to oxygen, that's a more interesting one, actually. We're in the p orbital, nitrogen versus oxygen. So we got like 1s2, 2s2, 2p what? 3, right? 1, 2, 3. Okay, there's nitrogen. Oxygen is just 1 to the right, right? So it has 2p4. 1, 2, 3. 1, 2, 3, 4. Okay? It's easier to remove that outer electron for oxygen. See the difference there? Because there's repulsion. Repulsion with this electron as its neighbor makes it easier. It's actually at a slightly higher energy level than the others. So you can remove that electron with less energy input. Okay, those are two. There are others, but we're not going to spend any more time on that one. We'll just call attention to exceptions when they occur and when we need to know them. Which atom requires more energy to remove an electron? Well, look, sodium and chlorine are in the same period. Which one's farthest to the right? Chlorine. So it takes more energy to remove the chlorine electron, the first electron, than it does sodium. How about lithium and cesium? Well, they're in the same group. Cesium is below lithium, so it's going to take less energy. Lithium takes more energy. Okay. Which has the larger second ionization energy? All right. So let's see. Where's lithium? There's lithium. First ionization energy is 1 electron. Now, when you remove an electron from lithium, it looks like helium. Right? It's got a perfectly filled outer orbital. You're into the core. Whereas beryllium, you got to get rid of 2 electrons. So the second electron is still part of the s orbital. It's easier to remove. So the larger second ionization energy would be lithium because we're getting into the core. Oops. This is just an illustration. This stair step shows you where the core electrons are. Okay, and we're going sodium, magnesium, aluminum, silicon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, all the way down to argon. So you have to remove more electrons to get into the core, is what that's saying. Just like that. Okay? Electron affinity. Electron affinity starts with the gas atom again. And now we're going to measure what is the strength of the attraction here. That gives you this ion. Now, when that happens, which way does the energy move? The energy moves out. As you add an electron, then you should get some energy out. So, the electron affinity is not exactly like ionization energy. I mean, it's not the reverse because we're not starting with an ion here. We're starting with a neutral atom. So it's a different concept. But it measures the strength of attraction of an atom for an electron. So as we go across a period from left to right, the electron affinities become more negative. Remember our convention with system? This is referenced here also to energy. So if energy leaves the system, it's negative. So the larger negative value means a larger E. You get more energy out for a stronger affinity. Right? I just wanted to make that point because it can be confusing. You would think, oh, it needs to be a bigger positive value. No, the bigger negative value means stronger affinity. So here when we say electron affinities become more negative from left to right, that is, the strength of attraction of an electron to a neutral atom across this period increases as you go left to right until fluorine is the most strongly attracted to an electron of all the elements in the periodic table. And down a group, the electron affinity becomes more positive. That is, the electron affinity decreases as you go down. So the negative number decreases, or you may become more positive, a positive number. So what's the general trend? The electron affinity increases from lower left to upper right, just like the ionization energy. But as it's measured, it becomes more negative from lower left to upper right, based on this convention. Okay. One more. Atomic radius. So I've always been puzzled how they determine the radius of an atom. Because we've already said we don't know where the outermost electrons are. It's probability. So how do you tell where the atom stops and where the next one begins? Well, that's the key. And it depends on the element and the phase. You have to make several measurements using different forms, and then you just got to pick and choose. Which one do you want? But in general, if you use the similar methodologies for determining the atomic radius, as you go across the period from left to right, the radius decreases. And that's generally true, especially if you stay in what we call the representative elements. Those that fill the s orbitals and the p orbitals are called representatives. And if you go from left to right in the representatives, you find that the radius decreases. So you would expect fluorine to be a smaller radius than lithium, and it is. And that's predominantly due because you're increasing the effective nuclear charge, more protons in the nucleus, and they're drawing the electrons in. As you go down in a group, you're increasing the size of the atom. And that's simply a consequence of adding energy levels. Okay. So shrink the atom from lower left, from bottom to top, and from left to right. But general atomic radius increases in going down a group. Yeah, they're bigger down here and smaller up there. So lower left to upper right, you decrease the radius. Okay? And this is like a pictorial representation. And notice they only use the representative elements here. The 1, 2, the A's. When you get into the transition metals, they kind of go, they're a roller coaster. So they don't fit the trend very well. Let's see. We'll get the bearings here. We're about done with this one. Which should be a larger atom, right? Sodium or chlorine. There's sodium and there's chlorine. Sodium ought to be bigger. And it is. Now, why do models, representations of sodium chloride always show the sodium like this and the chloride like that. Why do they make the chloride bigger than the sodium? We're talking about neutral atoms here. When you get to this point, you've lost an electron and it's ended up over here. So this one shrinks that size and balloons this size. Okay, so that's why they show them the chloride atom is bigger, the ion is bigger than the sodium ion. So that's the point I'm making is we're talking about neutral atoms here. We're not talking about ions. Ions is a different story. Which one of these is larger? Well, I would think cesium would be. More energy levels, more electrons. Yeah, it should be huge by comparison. Okay. Oh, this is interesting. When we're looking at the orbitals themselves, now this is in general terms, right? We don't actually know the size of the orbital, not in a definitive way, because Heisenberg said you can't know it. But in general, which should be larger? The hydrogen 1s orbital or the lithium 1s orbital? Think about it this way. Who's got more protons? Lithium's got 3, hydrogen's only got 1. So hydrogen should have the larger 1s orbital. Oops. And which has lower energy. Lithium would have the lower energy because it's closer to the nucleus. If it's a smaller orbital, it would be closer, lower energy. All right. Oh, I think they were going to show us one way that they determine radius of an element. And let's see, this is 213. Yeah, 214. One of the first things we do in 214 is we jump on this crystal lattice structure thing. And that's one of the ways to determine atomic size. Okay. I know you can hardly wait. And you have to do it different with metals and nonmetals. Right? There's just little commonality there. So it's kind of a, I don't know, it's as much art as it is science. How about these elements? Oxygen, fluorine, and sulfur arranged in order of increasing ionization energy. Right? Lower left to upper right increases. So there's oxygen, there's fluorine, and there's sulfur. So it should be sulfur, oxygen, fluorine, increasing ionization energy. What atomic size? Well, let's see. I would think that sulfur would be bigger, oxygen, and then fluorine would be smaller. So we're increasing, that means it'd be opposite. Yeah. All right. Final thoughts. It's the number and type of valence electrons that primarily determine an atom's chemistry. That is true in spades. The valence electrons are the ones that participate in reactions. Electron configurations can be determined from the organization of the periodic table. Well, that's true too. Okay. I'm glad you can do it that way because I don't want to have to sit there and use all those rules to get where I'm going when I've got a periodic table that shows me where everything is. Certain groups in the periodic table have special names. Well, yeah, we didn't go over them, but let's see. Didn't we have extra credit where you draw the table?
For the alkaline earth metals and all that, transition metals.
Or maybe I didn't give that one to you.
Halogens and all that stuff.
Maybe this is where I'm going to give that one to you. Right? Where you have a blank table and you fill in the elements?
Yeah, we didn't fill them in, did we? Yeah, we did.
See, I never got that paper, but I don't.
Oh.
I guess it was, or I might have missed it, not picked it up.
Okay.
I did the other extra credits.
I
The
filled
naming
in,
one.
And then we had the color,
The colored, yeah, where you get out your colored pencils. Okay. Okay. So you already know about those special
You know,
names.
like alkaline metals and stuff like that, right? Halogens and calogens and stuff.
Chalcogens are oxygen group, pnictogens are the nitrogen group.
Because I had to name them all and color them all, and I didn't color very good, but I tried. I only had crayons. so
Right.
I had to-
Well, this is not ARC 10. This is not ARC 213.
You wouldn't want me in art.
No, me either. I mean, I'm not a feeling type of person for art. I mean, it's more,
I can see art and think that it looks good, but I cannot make art.
yeah, I'm with you there. Okay, so, basic division of elements in the periodic table, metals and non-metals, we talked about that. There's this one has a red line, and you go between boron and aluminum, and then you start stepping down. Aluminum, silicon, split, silicon, germanium, germanium, arsenic, and there's a zigzag that goes right down there. On the right is non-metals, on the left is metals. So most of the periodic table is metals.
Is it clams or oysters that have the pearls?
They have what?
They have the pearls.
Oysters.
Oh, the oysters.
Yeah. You know, I think both mollusks can produce.
I think
Pearls.
because I think I've heard like a clam doing it before.
Yeah, yeah. It's a defense mechanism. When they get grit and stuff inside the shell, they surround it with that compound to keep it from irritating.
I have a silver pearl on my keychain because I went to Myrtle Beach for Myrtle Beach for vacation this year,
Uh-huh.
and I had $5 to open an oyster because they had an oyster farm, and I got him to open one. He said, "What color do you think the pearl's going to be?" I said, "I ain't got a clue." He opened it. It was a silver one. It's on my keychain now. It's the top of the pearl.
Yeah. Yeah. I think they even have some black ones.
Yeah, they're really rare. They said the black ones were. He said, "I've only got 5 of those today."
Mm-hmm.
It was like at 5 o'clock in the evening. There's a lot of them. He was gone, I think.
Mm-hmm.
There's blue ones and orange ones. I was just sitting there like, how do they make blue ones?
And they're not always round, right?
Yeah.
Mm-mm. You have to make them round.
Which one is in the conch shells? Like the big, they're real nice shells and they're pretty looking.
Yeah.
I know I went to the Bahamas whenever I was younger, and they were like mass harvesting out of the ocean, all these conch shells, and the slimy thing they pulled out of it, they cook up and they make, no, it wasn't a hermit crab.
Crabs and like snails live in those.
It was,
Well, that's a mollusk.
they produce the pearls too, but they're rare, they're more rare.
Yeah.
Than the pearls in the.
Oh, okay.
So,
Okay.
but they were good, they tasted good.
Yeah.
I went to the Bahamas when I was little. I
Yep.
can't remember I was really young.
They're like big snails.
Yeah.
Uh-huh. They're all
Almost like slug.
gastropods. They call them gastropods, which is Greek for stomach foot. So they crawl on their stomach.
Yeah.
That's their foot.
There's a slug that lives on the bottom of the ocean. I forget what they call it. But it looks like I forget what it is, but it looks like a bunny.
Really?
Yeah, it's like shaped like a bunny. I literally think they call it the bunny slug or something like that.
Okay.
And it was like pink in color and it was shaped like a bunny.
Mm-hmm.
It was a weird looking one. I didn't ever see one in person, but I was looking on the internet. It just popped up and I was like, huh.
They got a class of them called Nudibranchs, which is branch refers to long and nuda refers to naked. So they're the part of their structure that gathers oxygen from the water is this branching feathery thing that sticks out the back, and they circulate their blood through it, and they pick up oxygen from the air, from the water.
And it's kind of scary to look at.
Yeah, there's a lot of scary
It's so
stuff.
weird how you can bring a blobfish out of the ocean and it just looks completely different than what it's supposed to. We're done.
Yeah.
Yeah, that last slide, I always forget to get rid of it. It starts talking about individual groups and their characteristics, and we just don't have time for that.